This is a video about the universal gravitational force in one dimension. What we'll do is look at the formula first for the universal gravitational force. And this is it. It says the force due to gravity anywhere in the universe is equal to the universal gravitational constant, which is equal to 6.67 times 10 to the minus 11th meters cubed per kilograms second squared. So that's true all times, so that's constant. M1 and M2 are the masses in kilograms. R is the distance between the centers of two masses. So if we were to ask the question, what is the force due to gravity on the Earth by the Moon? Let's draw out the Earth first. The Earth is roughly 5.97 times 10 to the 24th kilograms. The Moon is 7.34 times 10 to the 22nd kilograms. And they're about 3.84 times 10 to the 8th meters apart. So plugging into our equation here for the universal gravitational force, G goes right into there. Okay, it's that value there. It'll always be the same. One of the masses, in this case the Earth, is plugged in there for M1. The other mass is plugged in there for M2. And the distance between them is plugged in the denominator. And really important, make sure it gets squared. The force experienced by the Earth from the Moon is 1.97 times 10 to the 20th newtons. What is the force due to gravity on the Earth by the Moon? So that would be in this direction. So that direction would be to the right, so we would consider that a positive 1.98 times 10 to the 20th newtons. And that's just based on the way we drew this picture. If we were asked, what is the force due to gravity on the Moon by the Earth, it would be in the exact opposite direction. That would be negative 1.98 times 10 to the 20th newtons. Now this is a third law effect. The force that the Earth applies on the Moon is equal and opposite to the force that the Moon applies on the Earth. So this is true from Newton's third law. Now we're going to do an example where we've got to apply the force toolkit. So you should already be familiar with all of these steps, and we'll apply them now. So let's say we have these three masses. Mass A, that's 363 kilograms. Mass B, that's 517 kilograms. And mass C, that's 154 kilograms. And let's say that between the centers of A and B, there's a distance of 0.500 meters. And between the centers of object B and C, there's a distance of 0.250 meters. And we're asked to find the net gravitational force acting on mass B. Step one would be to find what is our accelerated system. In this case, our accelerated system is the mass B. Number two would be to determine the coordinate system. So in other words, what direction is positive? And for us, in this very simplistic situation, to the right is positive. There's no up and down. We're pretending we're in deep space. So there's no normal force in this case. For number three, we would draw a force diagram. And this force diagram is a very simple force. This means the force that object C applies onto object B, and that is to the right. And this means the force that object A applies onto object B, and that, of course, is to the left. We write down Newton's second law, and in step 5, we plug in the equations that we used from step 3. So we simply plug those equations into here where we add up the forces. In this case, it's just the force of object A onto B and the force of object C onto B. And in step 6, we write out the universal gravitational force equation that we got earlier. And we start to plug in our equations, or plug in our values. So the universal gravitational constant is 6.67 times 10 to the minus 11 meters cubed per kilograms second squared. And since we're looking at the force that A applies to B, that would include mass A and mass B. And we divide by the square of the distance between them. And in this case, we get 5.07 times 10 to the minus 5th newtons. Now, we also need to get the force that C applies to B. Again, because of the universal gravitational force equation, we plug in the universal gravitational constant. We plug in the mass of object C and the mass of object B, and we divide by the square of the distance between them. And in that case, we get 8.497 times 10 to the 7th, 8.497 times 10 to the minus 5th newtons. So we add up those values, and when we add them up, we have to remember that we need the right direction, because the force of object A onto B is to the left. That's got to be a negative value. The force that C applies onto B is to the right. We plug that in as a positive value. The resulting force is positive 3.49 times 10 to the minus 5th newtons, and it doesn't hurt to say that that is to the right.